In this video, we'll be factoring binomials. A binomial is a polynomial with just two terms. Always, when you're factoring a polynomial, start by looking for a common factor. Turns out with binomials, you'll actually see this fairly frequently, especially in higher level classes. If there is none, or if you actually already have factored the common factor out, then the next thing to look for are perfect squares, because there's a special way that you can factor with perfect squares if it's in a binomial. You can also factor binomials that have perfect cubes, but that's not going to be required for this class. I will link to a video if you're curious about how to do it, but I'm going to stick in this video to perfect squares. Now, there are two things you can see when you have two perfect squares. You can either see them added together, so a squared is a perfect square, b squared, and added together, or you can see them subtracted. When they're added, they're called the sum of squares because you're adding. It turns out sum of squares is prime. It will not factor further. The difference of squares when you're subtracting will factor. Specifically, we factor into what we call conjugate pairs. So what you would have is you would undo the square that you see. So you'd have a and then b in both your binomials. And then you put one of each sign in. So these two factors look almost identical except for the sign change in the middle. That's what we call conjugate pairs, when the binomials look exactly the same but have opposite signs connecting the terms. So these are conjugate pairs. Now, again, you have to have squares for this to work. Again, to know it's prime, you have to have the sum of squares. To know it's a different, to be able to factor it as a different squares, you have to know you've got squares. So one thing to kind of be aware of and have in your mind when you see binomials is know what perfect squares there are. So let's just create a list of them. A perfect square comes from taking a whole number like 1 and squaring it. So 1 squared is 1, another one, 2 squared would be 4, 3 squared would be 9. We could keep going. 4 squared is 16, 5 squared is 25, 6 squared is 36, keep going, 49, 64, 81, 100, 121, 144, 169 is 13 times 13. I don't have any others beyond that memorized. I'd have to just do a little calculation to find them, but there's a bunch, and these are the most common ones you might see. So it's handy to kind of have this list memorized. And until you have it memorized, just keep a list next to you so that you know when you happen to be looking at a perfect square. Now, I mentioned over here that the sum of squares is prime and the difference of squares is not. It factors. Well, why is that? Let's talk a little bit about that before we do examples. When you look at this scenario of a squared plus b squared versus a squared minus b squared, what we want to do is break those squares up. So when you think about breaking them up, the obvious way is to undo the square. So we undo the square into the binomials. With the difference of squares, what I showed you there was that it's a conjugate. The reason this conjugation of using opposite signs there works is when we FOIL this out, we're going to get a squared in the first positions. The outside is negative AB, the inside is positive AB. And so having opposite signs there means that these two middle terms are actually going to go away. And in the end, a positive times a negative gives us a negative b squared. So you get that a squared minus b squared, you get that negative, and the middle terms cancel out because of the alternate signs. If I were looking at the sum of squares, the only way to get a positive b squared when multiplying b and b would either be to use two positives or likewise use two negatives there. Well, if I use two positives and try checking it by FOILing, a squared is what I want to start with, but then I get ab for the outside and another ab on the inside and then b squared. I get the first term and the last term, but because these are the same sign, ab plus ab is actually 2ab. It is not going to go away so that instead you still have a middle term. It isn't going to help if you fix this and make them both minuses to create the positive b squared. If you make them both minuses, all that does is make these two middle terms negative, but then they still add up to something that is non-zero. So it's not going to help. So it turns out no matter what you do, if you have the sum of two perfect squares, you're not going to be able to factor it. So that's why sum of squares is going to be prime. It's not going to factor, and the difference in squares is going to factor using this formula. Luckily, that formula is pretty straightforward. So what it comes down to with binomials is you really just have to recognize when you have the difference of squares and then just factor it using conjugate pairs. Looking at some examples, let's see which of these three below. I've got x squared minus 25, x squared plus 36, and x squared minus 12. Which of those would factor? And let's factor it if it does. So x squared minus 25. X squared is a square, 25 is a square, and then there's the minus, so that is a difference of squares. So this should factor into x 5 and 5 when we square root 25, and then 1 of each sign. Doesn't matter whether you put the plus or the minus first. And then if we want to check that, x squared minus 5x plus 5x minus 25 when you FOIL, and notice those middle terms just go to 0, and then you've got your result. Next example, x squared plus 36. These are both squares, x squared and 36 are both squares, but there's a plus in between them. Remember, the sum of two squares is prime, so this is prime. Does not factor. Next example, again a binomial. The first term is a square, but 12 is not. So even though it's a minus, which we need for this situation, we don't have a perfect square here. Because there's no common factor, this again is prime. There's nothing we can factor there. So there's three examples, one where it's a difference of squares and factors, one where it's a sum of squares doesn't factor, and one where you don't have either the sum or the difference of squares, and therefore it doesn't factor either.